Thanks for the invitation. It's great to be here. So this is a joint work with Vagos Hadjiafratis, Sai Ganesh Nagarayan, who is in the audience, and Xiao Wong. Let me just tell you that we came up with this project while visiting Simons in past summer. And in particular, when we attended a talk by Matus Telgraski. So typically in mathematics, we are trying to approximate functions, let's say continuous function, using simple units. In particular, there is this well-celebrated result by Weierstrass, where a continuous function can be approximated by a polynomial with sufficiently large degree. So also in Fourier analysis, we know that continuous functions can be approximated by sums of sine and cosine, maybe infinite sums. And more recently, we are interested in neural networks and what these objects can approximate. So let me tell you that the units, the simple units that the neural networks use are, the most common are sigmoids and ReLU functions, which are called activations. So there is a very celebrated result by Sibenko in '89 that says that any continuous function can be represented by one layer neural network, one hidden layer neural network with sigmoid activations, and the width should be sufficiently large. Okay, after that, there are many improvements on this theorem. They have done it for other activation units. But the main weakness in this theorem is that in practice we have bounded resources, and we cannot afford to spend, let's say, millions of units just to approximate a function. So in practice we have bounded resources. And then the main question that we are dealing with in neural networks is the expressivity. In particular, which functions can neural networks approximate? And the main question is, should the topology of the neural network, should it be deep? Should it be shallow? So in particular, intuitively speaking, we believe that the deep neural networks have more power than the shallow ones. So you can think of, if you have one hidden layer neural network, then essentially the output of the neural network is just the weighted sum of some independent features. But if you have, let's say, more layers, essentially you have compositions, and you can think that the output is features of features and maybe of features if you have more layers, and these are not independent anymore. So back to our main question, okay, you have like a budget. Let's say we have 10 ReLUs. Okay, 10 ReLUs is nothing. It's more like a joke, but what should be the best way to, what would be the best topology for the neural network? In particular, because we care about theory, how we formally compare a shallow and a deep neural network. And the answer is that there are some depth separation results. Maybe one of the first results was in circuit complexity by Hastad. But after that, there have been many works in neural networks. In particular, there are many notions that capture the complexity of a function. And this notion of complexity is important to prove separation results. So essentially to distinguish deep and shallow neural networks. Let me highlight the first one, which is number of oscillations a function can create. This is what we are going to use in this talk. But there are also different notions of complexity. More recently, a very interesting and combinatorial paper was published in NIPS, I think, using fractals and so on and so forth. And so I guess there are two types of separation results in the literature. Those that work in the low regime, low depth regime. In particular, there is a paper by Egdan and Samir that says that, okay, if you have 3 layers, if you have depth 3 and polynomial in D units, you can approximate your function, but if you have two layers, you need exponential in D to approximate your function. And there are also results in the so-called high depth regime. In particular, Tegraski's result by 15 and 16. So it's a cold paper that says that given a classification task, if you have a neural network of depth L and width 2, you can do this classification task. But if you have, let's say, square root of L depth, then you need exponential in L width, so units, to do this classification task. So you can understand that we cannot afford to have this many units, because it blows up as L grows. So that was some introduction. So in particular, I will talk about the Tegraski's construction. So as I said, the complexity that we care about is the number of oscillations of a function. So I'll talk about the Tegraski's construction. Then I'll talk about our result and connections to dynamical systems, and then I'll do some recap and mention some future directions. So the Tegraski's construction, basically Tegraski used this simple function. It's a piecewise linear function. So you can represent this simple function as a one hidden layer neural network, and each layer has at most 2 activation units. In particular, only the hidden layer has 2 ReLUs. Okay, and then so what Tegraski did was essentially try to compute compositions of this function. So how you compute composition of this function? In particular, if you concatenate this neural network twice, you get the composition of F 2 times. If you concatenate 3 times, you get the composition of F 3 times, so on and so forth. And what he observed is that when you take the composition of this function with itself, 2 times you create 2 triangles. If you take your composition of your function 3 times, you create 4 triangles. And you may understand that if you take t compositions of this function with itself, you create 2 to the t minus 1 bumps, essentially triangles. So the number of triangles or oscillations grows exponentially with the number of compositions of this function. So informally, what was Tegraski's result? So Tegraski said that if you give me an L, I can create a neural network that has depth 2L and width 2. So every layer has at most 2 ReLUs. Okay, so that any neural network that has depth little o of L, it needs width at least 2 to the power of the ratio of big L and small l in order to approximate this function. In particular, if the width is less than or equal to this number, then you can show a lower bound in the L1 distance between the construction, this function f, and the whole class of neural networks. And the same holds for a classification task he provided. So what was the main idea? The main idea, as we said, is first to define a notion of complexity. In particular, this is the number of oscillations. So what he showed is the following. So if you have many layers in a neural network, then you potentially can have many oscillations. But if you have few layers, then you must have few oscillations. And also, functions that have few oscillations can poorly approximate functions with many oscillations. So this was his proof in a nutshell. Okay, so let's go back to Tegraski's construction. So he provided this triangle, okay, and he took compositions of this triangle. One of his main questions in his cold paper was to understand if this result holds for larger families of functions. So in particular, this construction, as you can see, is very artificial in the sense that there is heavily symmetric. And the question is, okay, suppose we tweak a bit the function. Should it still hold? Should it still be a valid construction to show the separation results? So the number of oscillations grows exponentially with the number of compositions. So I'll give you 1 minute because this is very important. So I have given you 3 functions here. And my question is, what do you think about these 3 functions? Are they, let's say, hard to approximate using a shallow neural network or not? In particular, all of them are piecewise linear. Okay? And the first one looks like a triangle. The second one looks like a triangle, but it has 4 pieces. And the third one has 3 pieces. So, okay, let me give you the answer. So the first one, yes, it turns out that it's a valid construction for to prove a separation result. In particular, if you take the composition of this function with itself, it grows, the number of oscillations grows exponentially. The second one, intuitively, again, it should be the case. So yes, it is the case. So if you take compositions of this function with itself, then it also creates exponentially many bumps. But the third one, it's not true. Okay, and the question is, okay, why? Okay, so provably, we can prove that this one does not create exponentially many oscillations. Okay, all of them are piecewise linear. Some people might say, okay, it has to do with ellipsis constant. Yes, I agree, it has to do with ellipsis constant, but can we have a formal result about this? Okay, so again, this is the construction of Telgraski's result. So how we came up with this project? So when I saw this function, immediately I asked myself a question. So this question was related to dynamical systems. So my question is, does this function has a point of period 3? This is what I asked while attending Telgraski's talk. So what is a periodic 3 point? So let me start about what is a fixed point. Everybody knows what is a fixed point. So in particular, if you start from 2/3 and you apply your function f, you end up in 2/3. Okay, so this is invariant under the function f. It turns out that there are also periodic 2 points. What does this mean? It means that if you start from 2/5, then you are in the first regime. So after applying f, you go to 4/5. Then you should be in the second regime. And if you apply f, you go back to 2/5. So in particular, 2/5 is a fixed point of f square, okay? But it's not a fixed point of f. So this point is a periodic 2 point for your function f. And then my answer was yes when I asked myself in Simons. Yes, there is a period 3 point. And this period 3 point, it's this one. If you start from 2/9, you are in the first regime. You go to 4/9, again in the first regime. Then 8/9, second regime. And then you apply f again, you go to 2/9. So it had a period, it has a point of period 3. So intuitively, what is a periodic point of period p? So f to the p, so it should be a fixed point of f to the p. And then the intermediate points, essentially the trajectory, is all these points are distinct. Okay, this is what a periodic p point means. And I can keep going. I mean, there is also a periodic point of period 4 if you start from 2/17, and also a periodic point of period 5 if you start from 2/33, and so on and so forth. So let me tell you about our result. So our result essentially extends Telgraski's result. So suppose you fix L, and suppose that you are given a function that has a point of odd period. Okay, then for any neural network of depth little o of capital L, as long as the width of your neural network. So the number of units per layer is less than or equal to rho to this ratio, where rho is a number that is between 1 and 2. Essentially, it's the root of this polynomial. So everybody can see that there is a root between 1 and 2 for this polynomial by Bolzano's theorem. For lambda equals 1, this is negative. For lambda equals 2, this is positive. Okay, there is always a root between 1 and 2. So essentially, you can show that if the width is less than this number, you cannot approximate your function. So some observations about our theorem. So it works for odd periodic points. Okay, so only odd periodic points can give us depth with trade-offs. Special case is when it's a period 3. So in this case, this rho is the golden ratio. So let me tell you just briefly that the number of oscillations, you can prove that the number of oscillations grows at least as a Fibonacci sequence for this particular case. And it turns out that if you have smaller periodic points, then you have more oscillations. Okay, so the smaller is p, the periodic point. The bigger is rho. So the more complex is the function. So in particular, let me go back to this slide. So the first one, as a function, is more complex than the second one. So the first function has a periodic 3 point, and the second one has periodic 5, and it doesn't have periodic 3, probably. Okay. So yeah, the first figure was more complex than the second. And also, if you don't have periodic points of odd period, in particular, if you have only periodic points of powers of 2, this is a counterexample. So let's go back to our figures. So the third one has a periodic point of period 4, okay, and probably doesn't have any periodic point of odd period. And you can show that the number of oscillations of the compositions of this function with itself grows linearly in the number of compositions. So it doesn't blow up as the other two cases. It doesn't grow up exponentially. Okay, so right. So highlight this one, periodic 3, because I will mention later a very strong theorem from dynamical systems. And then the crucial question is, are there constraints on the periods a function can have? Of course, okay. And we will see in a moment. So as I told you, when Telgrassky showed his construction, I came up with this question, if the function has period 3. So there is a well-celebrated result from 1975 by Lee York that says that if you have a function, a continuous function, let's say from a closed interval to itself, and this function has a periodic point of period 3, then this function satisfies the following properties. Then the function contains periodic points of any period. First of all, it's clear that it has a fixed point. Okay, you can show that in many ways. For example, because it's continuous, right? Brouwer fixed point, and even easier using Bolzano or whatever. But you can show that it has periodic points of any period, not only period 1. And also, for infinitely many points, if you just simulate your dynamical system, you will observe that the trajectories kiss and separate, in the sense that this is informal, but mathematically speaking, if you take the lim_inf and the lim_sup of two trajectories, the lim_inf is 0 and the lim_sup is greater than 0. So essentially, the two trajectories do this kind of, they do have this kind of behavior. But here is a plot twist. It seems that this is a special case of a theorem that was like 10 years, was proved 10 years ago than that one. But around that time, it was the Cold War, and it was very hard from the east side to communicate with the scientists from the other side. So what was this theorem about? So this is called the Sarkovsky's theorem. This is what we are using in our proofs, essentially. So what the Sarkovsky's theorem says, so let me first define you what is a Sarkovsky ordering. So you have the natural numbers. So you start, let's say, by ordering all the odd numbers in increasing order. Then you order all the odd multiples of 2 in increasing order. Then all the multiples of 4, the odd multiples of 4, and so on and so forth. And in the end, you put in decreasing order the powers of 2. So this is a valid enumeration of the naturals, okay? So it turns out that, suppose that you have a function f that is continuous from a closed interval I to itself. If your function has a periodic p point with period p, and p dominates p prime in that ordering, then your function has a periodic point of period p prime. So in particular, that's why I ask why this result implies the previous one. You see that 3 dominates all the other numbers. So if a function has a point of period 3, it should have a periodic point of any period. So essentially, as I told you, Sarkovsky's theorem implies the first bullet of Lee-York chaos theorem. So as I have described now what Sarkovsky's theorem says, I mean, to prove such a theorem, you can understand that you need the elementary mathematics, okay? But the techniques are far from trivial. So let me tell you how you prove such a theorem first, because we are not going to use Sarkovsky's theorem exactly for our theorem. We are going to use a key lemma in his proof. So, okay, how you prove Sarkovsky's theorem? Essentially, you have to create something that's called the covering relation. So suppose that you have 2 intervals, and these 2 intervals are interior disjoint, or let's say, or they coincide, they are the same interval. You put an arrow from interval 1 to interval 0, if and only if the image of the interval 1 is a superset of the interval 0. Okay? So again, the function should be continuous. And then under this covering, we call it covering relation, you can create a graph. Okay? So what is the idea of Sarkovsky's proof? Essentially, take a periodic point P and then order the points, let's say, in increasing order. This creates a partition of your domain. Okay, so define the intervals as you have put the points of the cycle in increasing ordering, and then if this is the key lemma in Sarkovsky's proof, if the periodic point is of odd period, then and you create this covering relation graph, you will always have a subgraph that is of this particular form. So what is this form? Essentially, you have p minus 1 intervals. Okay, you have an oriented cycle among these p minus 1 nodes in the graph, and you have a self loop in let's say in the node in the 0 node. And this self loop essentially is what makes the difference. Okay, so this self loop is what we are going to use to prove that the number of oscillations grows exponentially. So in a nutshell, in Sarkovsky's proof, there was a key lemma that was saying that if you create a graph from the covering relations of these intervals that are defined by the cycle, by the periodic cycle. So what is a periodic cycle? You take the periodic point and just order the intermediate points in increasing order. Okay. So this is always a subgraph of the covering graph, and So our key lemma for our result is the following. Suppose that you have a function from 0, 1 to 0, 1. So the 0, 1 to 0, 1 is not necessary. You can have any closed interval, okay? And suppose that your function p, your function f has a periodic point of odd period, and p is, the period is greater than or equal to 3. Then you can find some x and y so that your function oscillates between x and y. What does it mean oscillate? Let's say it starts from x, it visits y, then it visits x again, it visits y, and so on and so forth. And this happens at least c to the t times, where t is the composition, the number of compositions of your function, okay? And c is the root of this polynomial. So in particular, again, if p equals 3, this is the golden ratio. And as p is smaller, you have more oscillations. So you can show that c is decreasing in p, okay? So here is an example. So suppose I'm giving you this function. This is like a parabola. So it turns out that this function has a period 3 point. So then if you apply the composition of f 10 times, you expect to have like exponential with base the golden ratio and the power 10 number of oscillations, okay? In particular, you see how many oscillations you have, and I have just zoomed in between 0.8 and 1. So yeah, even in practice, you can see that how many oscillations are created. So let me tell you a bit about our proof. So as I told you, so I'll give you a direct proof for p equals 3, but this proof is easily generalized as you can, if you can understand the techniques. So in particular for p equals 3, if you write down the covering relations, okay, as we said, there is a subgraph of this form, okay. In particular, p equals 3, so you have two nodes, you have a directed cycle, and then you have a self loop in the initial node. Yes?
I missed the definition, but don't all the nodes have self loops?
Not really. So what is the definition of the edge? So it's this one. So the definition of an edge is the following. If the image of I1 is a superset of I0, you add an edge.
I thought I1 contains f of I0.
No, it's the other way.
What are the J, J, Ji's? What are the zeros?
So, okay, so let me, okay, because I skipped it a bit, but so as I told you, there are p minus 1 nodes. If you have a periodic p point, you have p minus 1 nodes, okay? In Sarkovsky's result, there was a key lemma that was saying that there is a subgraph of at most p minus 1. So you can have less vertices, okay? But you will have this structure, you will have at least 2 vertices, and it should be an oriented cycle plus a self loop, okay? So you might have less than p minus 1 nodes. Right, so what is the idea now? The idea is rather simple. From a graph, you create an adjacency matrix, okay? In particular, suppose you have 2 vertices, okay, and you have this graph, you can create the adjacency matrix. You put 1 if there is the edge, 0 if there isn't the edge. So the self loop is this particular one on top left. So this makes the difference, okay? Now what you can do is you can prove that the number of oscillations scales as the largest eigenvalue of a to the t, okay? So if you take compositions of ft times, the number of oscillations scales as the largest eigenvalue of a to the t. But what is the largest eigenvalue of a to the t? Is the largest eigenvalue of a to the power of t, okay? So we just have to compute the characteristic polynomial of a. In particular, for this simple adjacency matrix is lambda squared minus lambda minus 1. Now, and this gives you the golden ratio, okay? In a more general setting, where you have like, instead of 2 nodes, you have p minus 1 nodes, you can understand that the graph is like the generalization of this matrix. And you can prove that the characteristic polynomial of the big matrix is this one, lambda to the p minus 1 minus lambda to the p minus 2 minus 1. And this characteristic polynomial has a root always which is greater than 1 and less than 2. Okay? So that's why the number of oscillations grows exponentially with the number of compositions. And then, as you have proved that, this key lemma, you can construct a classification task. And this classification task, your function f succeeds with probability 1, but any neural network that does not satisfy the specifications fails with constant probability. Okay? And what is this classification task? Essentially, you have your x and y, and you have these oscillations, which are exponential in the number of compositions. And the classification task is just you make all these that are above x plus y over 2 to be plus 1, and those that are below minus 1. Okay? And you can prove that any neural network fails to classify at least, let's say, 10% of the points. So that's essentially the idea also behind Telgrassky's result. You might ask what happens when you have, what about A1 distance? In this case, under some further assumptions of the Lipschitzness of your function, you can also prove that the A1 distance is bounded away from 0 between your function and the class of neural networks you are interested in. Okay, so that was my talk for today. So let me do a recap. So what we saw today was essentially an application of a theorem from dynamical systems that is used in to argue about the expressivity of neural networks. And you can prove depth width trade-offs based on the notion of period and periodic points. So there are many directions, as you can understand. So what are the directions? So first of all, they have been suggested, as we said, a lot of notions, complexity notions of functions. Okay. In particular, they have talked about global curvature, number of oscillations. This result is about periodic points, trajectory length. So the question is there some unified theory that captures everything? So, so there is some notion that is called topological entropy, and it seems that this is the right notion because it seems that captures many of these complexity measures. And let me also tell you that this notion, it seems that has a lot of connections with VC dimensions. Okay, so the question is, can we create a general framework to prove, let's say, separation results using techniques from dynamical systems, maybe? And then, okay, the second question is much more complicated, I feel, because it's not about structure, it's also about optimization. Okay, these results are, the representation is just one thing. What about optimization? Okay, if you have some specifications about your neural network, can you say something about if it is hard or simply to optimize, to train this neural network? So, and I think I'm done. Thank you for your attention.